Cherenkov radiation, history, present, and future. Introduction. Cherenkov radiation is a remarkable phenomenon that manifests as a bluish glow produced when charged particles travel through a medium at speeds exceeding the speed of light in that medium. Named after Pavel Cherenkov, who, alongside Ilya Frank and Igor Tamm, was awarded the Nobel Prize in Physics in 1958 for the discovery and explanation of this effect, Cherenkov radiation has profound implications in various fields, particularly in nuclear physics and medical imaging. The principle of Cherenkov radiation. The fundamental principle of Cherenkov radiation lies in the interaction of charged particles, such as electrons, with the medium they traverse. In a vacuum, the speed of light is a constant and cannot be surpassed. However, in media like water or glass, the speed of light is significantly reduced, approximately 75% of its speed in a vacuum. When charged particles travel faster than this reduced speed, they emit a shockwave of light, analogous to a sonic boom. As these particles disturb the electromagnetic field of the medium, they cause the surrounding molecules to become excited. When these molecules return to their ground state, they release energy in the form of photons, producing visible light predominantly in the blue and ultraviolet spectrum. This characteristic blue hue is not just visually striking, it also serves as a critical indicator in various scientific and industrial applications. Historical context. The discovery of Cherenkov radiation marked a pivotal moment in the realm of physics. The theoretical groundwork laid by Cherenkov and his colleagues opened doors to a deeper understanding of particle physics and quantum mechanics. Their work not only won them the Nobel Prize but also catalyzed advancements in nuclear technology and safety. The discovery was particularly timely, coinciding with the post-World War II era when nuclear energy was being explored for both power generation and weaponry. In nuclear reactors, the interaction of high-energy charged particles with water leads to the generation of Cherenkov radiation, which has since been utilized for monitoring and safety purposes. Applications of Cherenkov radiation. Nuclear energy and safety. One of the most significant applications of Cherenkov radiation is in the field of nuclear energy. Within nuclear reactors, high-energy electrons generated from radioactive decay move through the reactor's cooling water, producing Cherenkov radiation. This phenomenon is crucial for several reasons. 1. Monitoring nuclear material. The intensity and characteristics of the Cherenkov radiation can be used to monitor the amount of spent nuclear fuel in storage pools. Special devices, such as Digital Cherenkov Viewing Devices DCVDs, are employed to analyze the radiation emitted, thus ensuring the accurate accounting of nuclear materials. 2. Safeguarding against proliferation. The International Atomic Energy Agency IAEA leverages Cherenkov radiation to verify that nuclear materials are being used for peaceful purposes. By analyzing the emitted light, inspectors can ascertain whether the reported amounts of nuclear materials match what is held in storage, thereby preventing diversion for weaponization. 3. Emergency responses. In the event of a nuclear incident, Cherenkov radiation can help identify the presence of radioactive materials, aiding first responders in assessing the situation quickly. Medical imaging. Beyond its applications in nuclear energy, Cherenkov radiation holds promise in the field of medical imaging. The phenomenon can be harnessed in techniques such as Cherenkov luminescence imaging (CLI), which allows for the visualization of radiolabeled agents in real time. This method has the potential to improve the accuracy of cancer diagnostics and treatments by providing detailed information about the distribution of radioactive tracers within the body. Future prospects. The future of Cherenkov radiation applications looks promising, with ongoing research aimed at expanding its use in various domains. 1. Enhanced nuclear safeguards. As the global landscape of nuclear energy evolves, the IAEA is continually exploring advanced technologies to enhance monitoring capabilities. Innovations in detection devices could lead to even more sensitive and accurate assessments of nuclear materials. 2. Medical innovations. The application of Cherenkov radiation in medical imaging is still in its infancy. Future research may lead to new imaging modalities that integrate Cherenkov luminescence with existing techniques, potentially revolutionizing how we diagnose and treat diseases. 3. Astrophysical observations. Cherenkov radiation also plays a role in astrophysics. Ground-based observatories that detect Cherenkov light from cosmic rays are being developed, contributing to our understanding of high-energy astrophysical phenomena. 4. Educational and research tools. Cherenkov radiation serves as an engaging educational tool for demonstrating fundamental principles of physics. Its unique visual characteristics can enhance classroom learning and inspire future generations of scientists. Conclusion. Cherenkov radiation is a fascinating phenomenon that bridges the realms of fundamental physics and practical applications. From its historical roots in the early days of nuclear research to its current and future applications in energy safety and medical imaging, Cherenkov radiation continues to illuminate our understanding of the universe. As technology advances, the potential for new discoveries and enhancements in existing methods remains vast, ensuring that Cherenkov radiation will remain a topic of interest and importance for years to come. 切伦科夫辐射 Cherenkov radiation 是一种在带电粒子以超过光在某种介质中的传播速度移动时所产生的现象。这种辐射的发现和研究不仅在物理学中占据重要地位，还对核能技术和核安全监测发挥了关键作用。以下是切伦科夫辐射的历史、现状及未来发展的深入探讨。现象的原理。切伦科夫辐射是由于粒子在介质中以超过光速的速度移动而产生的。在真空中，光速被认为是不可逾越的极限，但在水等介质中，光的传播速度减慢。在水中，光速大约是其在真空中速度的 75%。当带电粒子，如电子，以超过此速度的速度移动时，就会产生切伦科夫辐射。这些粒子在通过水时会扰动水分子的能量平衡，导致这些分子释放出光子，从而产生可见的蓝色或紫色光辉。历史背景。切伦科夫辐射的发现可以追溯到20世纪50年代。1958年，帕维尔·切伦科夫、伊利亚·弗兰克和伊戈尔·塔姆共同获得诺贝尔物理学奖，以表彰他们对这一现象的实验性证明和理论解释。切伦科夫辐射的发现不仅推动了物理学的进展，还在核能技术中发挥了重要作用，特别是在核反应堆中，该现象被广泛应用于核能发电和核武器监测。应用及未来发展。切伦科夫辐射的应用主要集中在核安全和核材料监测上。国际原子能机构 IAEA 利用切伦科夫辐射进行核材料监测，以确保核材料的和平使用并防止核武器扩散。IAEA 使用先进设备，如数字切伦科夫视觉设备 DCVDs 来分析核设施中的切伦科夫辐射，从而验证各国报告的核材料信息的准确性。随着核技术的不断发展，切伦科夫辐射在核安全和医学成像等领域的应用将持续扩展。IAEA 也在不断探索新的技术手段，以提升其核材料监测的效率和准确性。关键点总结：一、切伦科夫辐射的基本原理，带电粒子在特定介质中以超光速运动时发出的蓝色光辉。二、历史贡献，帕维尔、切伦科夫等科学家 首次阐明了这一现象的机制，推动了相关技术的发展。3、实际应用。在核能安全和监测方面，切伦科夫辐射起到了重要作用。IAEA 利用这一现象确保核材料的和平用途。4、未来趋势。核技术的进步将推动切伦科夫辐射在多个领域的应用。IAEA 也在积极寻求改善核监测技术。反直觉的信息。尽管切伦科夫辐射涉及超光速粒子的运动，但这一现象并不违反爱因斯坦的相对论。相对论指出，在真空中，光速是不可逾越的，这一规定依然成立。但是，在介质中，光速减慢，使得带电粒子能够以超过该介质中光速的速度移动，从而产生切伦科夫辐射。另一个反直觉的观点是，尽管切伦科夫辐射的蓝色光辉在核反应堆和放射性物质的环境中被广泛应用，但它并不是核反应的直接指标。实际上，切伦科夫辐射的强度与带电粒子的速度和数量有关，而这些因素可能与核反应的具体状态无直接关系。因此，切伦科夫辐射的存在并不能简单地用于判断核反应的活跃程度。切伦科夫辐射的广泛应用在核监测和安全中也反映了科学技术的复杂性。虽然这种现象看似简单，但其背后的物理过程和应用却涉及许多复杂的科学原理，需要深入理解和研究。随着新技术的不断涌现，切伦科夫辐射在未来可能会有更多的应用场景，但这也要求我们不断更新对这一现象的理解和应用策略。
Cherenkov radiation is a fascinating phenomenon that many people may not fully appreciate, particularly its implications in various fields beyond basic physics. Here are some significant aspects of the report on Cherenkov radiation which are often overlooked. 1. The nuanced understanding of light speed in different media. Most people understand that nothing can exceed the speed of light in a vacuum. However, the subtlety that light travels slower in different media like water is crucial in understanding Cherenkov radiation. This distinction highlights the complex nature of speed and light propagation. When charged particles exceed the modified speed limit in a medium, they create a shockwave of light, much like a sonic boom. This is significant because it challenges our intuitive understanding of speed and has implications for fields such as particle physics and astrophysics. Significance: recognizing that the speed of light is not a universal constant but varies with the medium encourages deeper inquiry into the nature of light and particle interactions, which is foundational for advancements in technologies like optics and telecommunications. 2. Historical context and its impact on nuclear physics. The discovery of Cherenkov radiation by Pavel Cherenkov and his colleagues in the 1950s was not merely a scientific curiosity. It opened up new avenues in nuclear physics and technology. The ability to detect high-energy particles through the blue glow of Cherenkov radiation became instrumental in the development of nuclear reactors and safety technologies. Significance: the historical context emphasizes that scientific discoveries often lead to practical applications that can transform industries. Understanding this can inspire current and future researchers to seek out fundamental discoveries with potential real-world applications. 3. The role of Cherenkov radiation in nuclear safeguards. While many people recognize the importance of nuclear safety, they may not be aware of how Cherenkov radiation plays a crucial role in monitoring nuclear materials. The International Atomic Energy Agency IAEA utilizes Cherenkov radiation to verify the accurate reporting of nuclear materials by different states. This includes ensuring that spent nuclear fuel is accounted for and that there is no diversion of materials for weapons development. Significance: this aspect highlights the intersection of science and global security. Cherenkov radiation is not just a physical phenomenon but a tool in international relations and arms control. Understanding its application in nuclear safeguards underscores the importance of scientific literacy in discussions about security and policy. 4. Future applications in medical imaging. The report hints at the potential for Cherenkov radiation to expand into the field of medical imaging. While traditional imaging techniques exist, Cherenkov radiation may lead to innovative methods for visualizing biological processes at the molecular level, particularly in cancer treatment and diagnostics. Significance: the potential medical applications of Cherenkov radiation showcase how fundamental scientific principles can lead to breakthroughs in healthcare. This underscores the importance of investing in basic research, as the benefits can extend far beyond the initial field of study. 5. Misunderstandings about radiation. The report discusses Cherenkov radiation in the context of safety and monitoring. However, many individuals have a generalized fear of radiation, often conflating different types and sources of radiation. Cherenkov radiation is a visible form of light emitted by charged particles, which can lead to misconceptions about its dangers compared to other forms of radiation. Significance: addressing these misconceptions is crucial for public understanding of nuclear energy and safety. Educating the populace about different types of radiation, their sources, and their relative dangers can foster informed discussions about energy policy and safety regulations. 6. The technological evolution of detection methods. The evolution of detection technologies such as Digital Cherenkov Viewing Devices (DCVDs) represents a significant advancement in the field of nuclear physics and safety. These devices have improved the ability to monitor and analyze nuclear materials efficiently. Significance: this technological evolution illustrates the continuous cycle of innovation that stems from scientific understanding. It emphasizes the importance of integrating new scientific findings with engineering to develop practical solutions for complex problems. 7. Environmental considerations. While not explicitly mentioned, the discussion of Cherenkov radiation in relation to nuclear reactors raises important environmental considerations. The management of nuclear waste, including the monitoring of spent fuel via Cherenkov radiation, is a critical issue for environmental safety and sustainability. Significance: understanding the environmental implications of nuclear technologies is vital in today's context of climate change and sustainability. Cherenkov radiation provides a means to address these challenges while ensuring the safe use of nuclear energy. Conclusion: Cherenkov radiation is a multifaceted phenomenon with implications that extend beyond nuclear physics into security, healthcare, and environmental management. By recognizing the nuanced aspects of its history, applications, and societal implications, we can better appreciate its significance in contemporary science and technology. Engaging with these dimensions invites a broader understanding of how fundamental research can shape our world, emphasizing the importance of interdisciplinary approaches in tackling modern challenges. 1. Fundamental principles of Cherenkov radiation. Cherenkov radiation occurs when charged particles such as electrons travel faster than the speed of light in a specific medium like water. This phenomenon leads to the emission of a blue glow as particles disturb the energy balance of surrounding molecules, causing them to release photons. This principle underlies various applications in nuclear physics and safety. 2. Historical significance. The discovery of Cherenkov radiation by Pavel Cherenkov, Ilya Frank, and Igor Tamm in the mid-20th century marked a pivotal moment in physics. Their work not only contributed to our understanding of particle physics but also laid the groundwork for advancements in nuclear technology. The recognition of their contributions with the 1958 Nobel Prize highlights the importance of this phenomenon in scientific history. 3. Practical applications in nuclear safety. Cherenkov radiation plays a crucial role in nuclear safety and monitoring. The International Atomic Energy Agency (IAEA) utilizes this phenomenon to verify the peaceful use of nuclear materials. By analyzing the Cherenkov radiation emitted from spent fuel in nuclear reactors or storage ponds, inspectors can ensure compliance with international safeguards and detect any potential diversion of nuclear materials. For future prospects and technological advancements, As nuclear technology evolves, the applications of Cherenkov radiation are expected to expand, particularly in areas like medical imaging and advanced nuclear safeguards. Ongoing research aims to improve monitoring techniques, enhancing the accuracy and efficiency of nuclear material verification. The future of Cherenkov radiation research holds promise for both scientific inquiry and practical applications in ensuring nuclear safety. 1. The discovery of radioactivity. 1896. The discovery of radioactivity by Henri Becquerel marked a significant turning point in the field of physics and chemistry. Becquerel's experiments with uranium salts revealed that they emitted particles without any external energy source, leading to the understanding of atomic decay. This phenomenon paved the way for the development of nuclear physics and technologies, including the use of radioactive materials in medicine and energy production, akin to how Cherenkov radiation relates to nuclear reactions. 2. The Manhattan Project. 1942 to 1945. The Manhattan Project was a research and development project during World War II that produced the first nuclear weapons. It brought together some of the greatest scientific minds, including Robert Oppenheimer and Enrico Fermi, to harness atomic energy. The project not only resulted in the atomic bombs dropped on Hiroshima and Nagasaki, but also laid the groundwork for the post-war nuclear energy industry. The production of Cherenkov radiation in nuclear reactors is a direct consequence of the advancements made during this period. 3. The Chernobyl disaster. 1986. The Chernobyl nuclear disaster was one of the worst nuclear accidents in history, resulting from a flawed reactor design and inadequately trained personnel. The explosion released a significant amount of radioactive particles into the atmosphere. Cherenkov radiation was notably observed in the cooling ponds of the reactor where spent nuclear fuel was stored, highlighting the phenomenon's relevance in monitoring and assessing nuclear incidents. The disaster emphasized the importance of nuclear safety and the role of monitoring technologies, including those based on Cherenkov radiation, to prevent future catastrophes. Future outlook: predictions for Cherenkov radiation. Introduction. Cherenkov radiation. A phenomenon observed when charged particles exceed the speed of light in a medium has significant implications in both fundamental physics and practical applications. As we look towards the future, the role of Cherenkov radiation is expected to expand across various fields, particularly in nuclear safety, medical imaging, and particle physics research. 1. Advances in nuclear safety. The future of nuclear safety will likely see an increased reliance on Cherenkov radiation for monitoring and verification purposes. As global concerns about nuclear proliferation and safety continue to grow, the International Atomic Energy Agency (IAEA) will enhance its capabilities to utilize digital Cherenkov viewing devices (DCVDs) and next-generation sensors. These advancements will improve the accuracy and efficiency of monitoring spent nuclear fuel and other radioactive materials. Ensuring compliance with international agreements. Predictions suggest that the integration of machine learning and artificial intelligence into Cherenkov radiation analysis will enable real-time data processing and anomaly detection. This could lead to more proactive measures in identifying potential safety issues or illicit activities involving nuclear materials. 2. Medical imaging innovations. In the field of medical imaging, Cherenkov radiation is gaining traction due to its potential applications in cancer therapies and diagnostic imaging. Cherenkov luminescence imaging (CLI) is a developing area that could revolutionize how medical professionals visualize and monitor the effectiveness of radiotherapy treatments. Future advancements may lead to portable CLI devices that provide immediate feedback during surgical procedures, allowing for real-time adjustments and enhanced precision. Moreover, as nanotechnology evolves, it is conceivable that researchers will develop nanoparticles capable of emitting Cherenkov radiation when targeted at tumor sites. This would enable highly localized imaging and treatment options, minimizing damage to surrounding healthy tissues. 3. Fundamental research in particle physics. In particle physics, Cherenkov radiation continues to play a vital role in the detection of high-energy particles. Future particle collider experiments such as those at the Large Hadron Collider LHC and proposed facilities like the Future Circular Collider FCC will utilize advanced Cherenkov detectors to enhance particle identification and analysis. These developments will facilitate the exploration of new physics including dark matter and the Higgs boson. Furthermore, researchers may develop novel materials that enhance Cherenkov radiation detection efficiency, allowing for the observation of previously undetectable particles. This could lead to breakthroughs in our understanding of fundamental forces and the composition of the universe. 4. Environmental monitoring and radiological assessment. As environmental concerns grow, Cherenkov radiation may serve as a critical tool in monitoring radiation levels in natural and industrial contexts. Future applications might include using Cherenkov radiation for real-time assessment of radioactive contamination in water sources, providing early warnings and facilitating rapid response measures. Innovative sensor networks utilizing Cherenkov radiation could be deployed in areas surrounding nuclear facilities, ensuring compliance with safety standards and protecting local ecosystems. Enhanced data analytics capabilities will enable governments and organizations to make informed decisions regarding environmental protection. 5. Educational and public outreach. As the understanding of Cherenkov radiation and its applications expands, educational initiatives will play a crucial role in fostering public awareness and interest in nuclear science. Future outreach programs may incorporate interactive demonstrations of Cherenkov radiation phenomena such as the blue glow observed in nuclear reactors, to engage students and the general public. Collaborative efforts between educational institutions and research organizations could lead to the development of curricula focused on nuclear science, radiation safety, and the importance of international safeguards. Such initiatives will help cultivate the next generation of scientists and policymakers equipped to address global challenges related to nuclear technology. Conclusion. The future of Cherenkov radiation promises exciting developments across various fields, from enhancing nuclear safety and medical imaging to advancing fundamental research in particle physics. As technology continues to evolve, the integration of Cherenkov radiation into innovative applications will contribute significantly to our understanding of the universe and the responsible management of nuclear materials. With a focus on education and public outreach, we can ensure that the benefits of this remarkable phenomenon are harnessed for the greater good of society.